Okay, for example, some examples here with regards to picking the correct buffer pair. We've talked about the bicarbonate buffer system in the blood, and that's basically going to be between carbonic acid and bicarbonate, carbonic acid and its conjugate, bicarbonate. And this is one of those amphoteric ones where you can add an H, take away an H, you can go both ways, so it's a really good one for the blood system. But the Ka is 4.4 times 10 to the minus 7. So that means the pKa, the negative log of that, 4.4 times 10 to the minus 7, that's going to give you a pH of 6.35. So looking at this, and depending upon how you create your ratio, like this one's going to buffer closer to 7. And if you add a whole lot more of the conjugate in there, of course, that's going to increase the pH because that's the one that's acting like a base. So that's one example of how you would pick a buffer pair. So for instance, because the blood needs to remain between like 7.3 to 7.4 in the pH range, this one does have a significantly higher amount of the bicarbonate in the pair as well to make sure that it stays within that range. Now, you've got the lungs and you've got the kidneys and stuff trying to maintain the correct ratio of both of those through breathing, where carbon dioxide reacts with water to form carbonic, and then you also have excretion of the ions as needed, through the kidneys to leave the body to keep the correct ratio in place and maintaining the correct pH level of the blood. So that's one good example there. Another good example for different ranges, like, if you wanted it a little bit lower, acetic acid, acetic acid's good. That's this one with acetate as its conjugate. That one, the Ka, we know is 1.8 times 10 to the minus 5, and the pKa, of course, would be 4.74, so that one's going to buffer more around a 5-ish area, like so. There's also ones that can go even lower. Chlorous, for example, chlorous acid happens to be HClO2, so that means it would be HCl minus as its pair, and the Ka being 1.1 times 10 to the minus 2, so the pKa of this one is going to be 1.96. So this one's going to buffer more at a lower pH range. And last example I wanted to talk about is one where you're going to go into the higher pHs. The higher pHs like ammonia and ammonium. That's the main, weak base example. That's the best kind of buffer up there to go over without getting into really long organic type molecules. However, you base it off of the Ka of the conjugate acid. So here we would find, this is 1.8 times 10 to the minus 5 for the Kb. Then you would find the Ka, which is 5.6 times 10 to the, let me write that down here, it's a little bit. So the Ka of ammonium is going to end up being 5.6 times 10 to the minus 10. So this is the one that you would do the pKa of, and you would notice it's 9.25. And so this would be a good one to use if you were going to buffer around a 9, or if that's what was needed for the experiment or the particular solution being created. These are different ways that you would look at picking your correct buffer pair to stick with for whatever was necessary, because certain things need to run at certain pHs, and so you would want to conduct your experiments, of course, accordingly based off of how to choose the correct buffer if you needed to have your reaction taking place in a certain pH level, where it's going to be maintained too. You don't want it to go up or down or whatever when you're doing your reaction. All right, now we're going to start looking at recognizing the buffer solution type problems. Now, hopefully you will have picked up on this from the titration curve problems, because in the buffering region, you always note that this is like partial neutralization here. Anytime where you're, adding a strong acid or a strong base to a weak acid or a weak base, it's going to only partially neutralize it. So that means you're going to create some conjugate in the process. But it doesn't necessarily have to be attached to a titration curve. So for instance here, consider a solution made by mixing 0.1 of hydrocyanic, right here, with 0.04 moles of sodium hydroxide in aqueous solution. Calculate the pH of the resulting solution. So now we can tell, if you look at the numbers, you're only adding 0.04 to something that's 0.1, only some of it's going to actually neutralize. That means the sodium hydroxide, or the hydroxide part, is going to turn all into water, but you are going to now have some conjugate base floating around. Now, as I told you before, you can calculate this in two different ways. So, wanted to look at here different ways that you can do it. Now, like I said, the Henderson-Hasselbalch one is the easier one. Henderson-Hasselbalch, because you just plug it into the equation. But you can do common ion equilibrium with these problems as well. It just takes a little bit of extra time. So I'm going to show you one example of how to do it using the common ion method. So once again, looking here at our reaction, before we start getting set up, we have our acid plus the hydroxide. This is the neutralization part that's creating over here the H off of the HCN, the OH here, that creates the water part. But the CN here now, that's going to be conjugate base left over on this side. So adding in the hydroxide, it produces the CN, the conjugate base. And if you have both the acid and the base in solution, it happens to be a buffer. So you need to recognize it as a buffer, and then you can go ahead and try to do or calculate the pH either using common ion equilibrium or the Henderson-Hasselbalch. So we're going to look here, before we can even do common ion or Hendy-Hass, we have to do the BCA chart. You've got to get the number of moles in solution. So you set up your reaction, go ahead and do that, write out your reaction, which is the HCN plus the hydroxide. That gives you the CN and the water. Now we don't really care so much about the water. Once again, that part doesn't really matter. But so beforehand, we're going to have 0.100 moles. And it's nice that this problem already gave it to us in moles. Sometimes they'll give you like a certain milliliter at a certain concentration, and you have to figure out the moles. And they told us also the moles of the hydroxide that's being added. So we have that here. And of course, starting off with no conjugate. Now the change, once again, look at which one's going to run out. The hydroxide value is lower, so that means it's going to run out. So that's when we subtract from our reactant side over here. Sorry, that would be a 0 there, not a 4. So minus 0.04 here. And then that's what gets added to the conjugate side, because that's how much conjugate's going to be created. Because this is 1-to-1. So for every one H that gets pulled off that combines with the OH to form water, that means one conjugate base also gets produced in terms of mole ratio. So then afterwards, go ahead and calculate here. And this should be 0.060. And this should be, goes down to 0. And then we have 0.04. So this is the basic setup here of the moles. So we figured out, yes, we have our conjugate base, we have our acid in solution, we have both of them present. Both of them are present, this is a buffer. And we need to treat it as such, that it's a buffer. All right, now to do common ion, like taking a look at how to do the common ion way. What you can set it up as an equilibrium expression, starting with the reaction. So we're going to start with our rice table. We have our HCN reacting with water. That produces the CN and the hydronium. So this is how you would look if you did common ion. You take this H, of course, it adds over here. That's going to give you your hydronium. And then you have your conjugate left over from the original acid. What you have to consider here is if you're going to do a rice table, you need it in concentration. Luckily, this is out of a 1 liter solution here. So this divided by 1 liter, of course, is going to be 0.060 molar. And this one divided by 1 liter equals 0.040 molar. So we already, can turn it into concentration. But if the liters were not 1 there, you still have to divide it and find the concentration before you could plug it into the rice table. Rice tables always have stuff in concentration. So here initially, what do we have? Initially, we have 0.060 molar of our HCN. Remember, the water really doesn't matter. And we have 0.04 of our CN. It's like the common ion that's initially in solution, and then starting out with 0 hydronium. So then you do your change, subtract X plus X here, and then we go rice is 0.060 minus X, 0.040 plus X, and X. So now that we have this set up, all we have to do is set up the KB or the Ka expression. Ka expression, yes. So here we would do, Ka equals concentration of the first product times the concentration of the second product over the reactant, the HCN, like so. And then we plug in our numbers. So I'm going to go ahead and do this right here. So actually, I'm going to do it down here. We have the 6.2 times 10 to the minus 10 equals x squared over, no, actually it's not x squared this time. That's right, because we have the common ion in there. So it's not going to be x squared. This is going to be 0.04 plus x times the other x over 0.060 minus x. Now we still get to use our 5% rule, so we can cross off both of these for the addition and subtraction. Both of them can get eliminated due to the fact that they're going to be too small, less than the 5% rule. Eliminate x, 5% rule, going to be too small, negligible, all those good words. So when we do our calculation here now, we will just do the 0.6 and the 0.4, and then you leave this x up here intact. The other x, that one is the one that matters, that counts. So after calculating this, our x, which happens to be our hydronium here, our hydronium, which is concentration that we need to figure out the pH, that is going to be 9.3 times 10 to the minus 10 molar. And then all we have to do at this point to figure out the pH is do the negative log of our hydronium That's going to give us the pH. So do the negative log of 9.3 times 10 to the minus 10. And you notice that this is going to be 9.03. That's the pH, 9.03. Okay, so that's how you would set it up. And as you can see, it takes a lot of work to do the common ion effect for that particular one, where you have to set it up, you know, with the hydrocyanic reacting with water, do the entire rice table, change everything over to concentration, set up the Ka expression and all that. Takes a lot of time to do that. So instead, I'm going to show you how to do it using Henderson-Hasselbalch here. All right, we're going to look at, now we're going to use the pH equals the pKa plus the log of the base over the acid. This is such an easy formula once you recognize that you have a buffer in solution because you have both components. So just recalling HCN, and it doesn't matter if you use the mole or the concentration, because remember, this part is just a ratio, so you don't have to change it to concentration here. Makes it easier, less steps. So here it was 0.060 mole, or because we divide it by the 1 liter, it is also molarity. So either way, it doesn't matter for this one. And this was 0.040 mole slash molarity because you divide it by the 1 liter. So either way you're looking at it, you can use concentration or mole here. I prefer to stick to mole because it's quicker. So all I have to do is then plug and chug, add everything in. We have our Ka 6.2 times 10 to the minus 10. So negative log 6.2 times 10 to the minus 10 here. And then we add in the log of the base. Here's our base, 0.040 over the acid, 0.060, this one. And then we just calculate. And you'll notice when you plug and chug in the calculator, you'll see that the pH is still 9.03, like so. So the second one here, this method using Henderson-Hasselbalch, definitely faster. But like I said, if you're in the middle of the AP exam and you forgot about Hendy-Haas and you started doing it the common ion way and set up the rice table, you're still going to get the same answer. It's just going to take you a little bit longer. 9.03. All right, let's look at this one. Exercise 3, calculate the pH of a solution made by mixing 0.2 mole of acetic acid, 0.030 mole of sodium hydroxide in 1 liter aqueous solution. So here, as you can see, once again, you should be looking at the numbers you're given. So we have 0.2 mole of our acetic acid, 0.030 mole of the hydroxide. This is a partial neutralization. That means a buffer is going to get created because we know acetic acid happens to be a weak acid. So we are going to be producing conjugate base in here, weak conjugate base. When you look at this and you can tell that this is a partial neutralization, you need to start off with a BCA chart. So we're going to go here BCA before, change after, write out the reaction here. We have our acetic acid reacting with the hydroxide. That's going to give us the water and the acetate. Don't forget looking at your reaction here, this H plus the OH, that's what gives you the water. And then of course the acetate here from the acid is what is formed on the other side. Now we're starting with 0.2 moles. BCA charts are always in moles because you're keeping track of the count here of reaction. This is because, remember, it's 1 mole of H plus 1 mole of OH gives you 1 mole of water. And so that's how the neutralization works. And then you go back later on and figure out the new volume and the new concentration when you're done at certain points during a neutralization reaction. All right, so here, of course, water doesn't matter. I'm going to cross that off. We're starting out with 0 acetate. So looking here, looking at your numbers, this one's the smaller one, that one's going to run out. So that's the one you subtract from both of your reactants, like so. That's what you add over here to your conjugate, because everything is 1 to 1, like so. And then we're going to end up with our 0.030 on this side. This cancels down to 0, and this is going to be 0.170. And now looking at what we've got, we have the acid, we have the conjugate base. So yes, we have a buffer solution. So you can go ahead and go straight to Hendy-Haas. This is what I would do. Straight to Hendy-Haas. pH equals the pKa plus the log of the base over the acid. And since this is a ratio, we don't have to change it back to concentration. However, in this particular case, the moles are the same as the concentration because it's out of 1 liter solution. So then we just plug everything in. So pH equals the negative log of 1.8 times 10 to the minus 5 plus the log of the base, 0.030 over the acid, 0.07. Go ahead and take a moment to calculate that. And you look here for your pH. After doing all those calculations, 3.99, like so. And these are, 2 significant digits, so we're just going to go out 2 decimal places here for our answer. So that is the easier, fastest way. Trust me, Hendy-Haas is the fastest, easier way. However, do have it in here to show you what it looks like to do the common ion effect, if you want to use that. So here, instead of, we did the BCA chart first, which is great. Okay, do that. Once again, it was out of 1 liter, so you change this over to molarity, right? And you still get your 0.170 minus x, 0.030 plus x. You need to write out your Ka expression. Then you plug in your numbers, and you get to do the eliminate x for the addition and subtraction one. The eliminate x here, because that's going to be less than the 5% rule. It's going to be negligible or too small. And then you end up calculating x, which is the hydronium here. That's the important part. This x value is giving you the hydronium. And that's what we want, so that's what you're focused on. And once you get that value, you can do the negative log, and you end up getting your 3.99 pH there. So keep that in mind. You can do it this way. This way, though, as you can see, has a lot more work to setting it up. So the second you recognize you have both components, the acid and its conjugate, or the base and its conjugate, in solution, then it's a buffer. Remember, buffers are only going to be weak acids with their conjugate or weak bases with their conjugate. Strongs do not create buffers because they have neutral cations, neutral anions in their formulas, the strong acids and bases. They will not create buffers because their prospective other component, their conjugates, do not react with water and they stay neutral. All right, now calculate the pH of a solution made by mixing 100 milliliters of 0.1 solution of acetic acid. It has a Ka value of 1.8 times 10 to the minus 5 and 50 milliliters of 0.1 solution. So this time they gave us actual volumes. I'm going to go ahead and definitely look at calculating the moles first, because we need to do the BCA chart to figure out what's still in solution. So 100 milliliters of 0.1 being mixed with something that's 50 milliliters of 0.1 is definitely a partial neutralization. So let's take a look there. And I'm going to also embrace using the millimole here. Okay, millimole over milliliters. Okay, definitely the way to go here to make your numbers easier to work with. So for our 100 milliliters of 0.1 of the acetic acid, we're going to do the 0.100 equals the millimole over 100 milliliters. That's going to give us 0.1 times 100. That's going to give us 10 millimoles of acetic acid. And also remember, acetic acid can be written like this. That's the organic way, where you would take off this H as the one to remove it for the acidic H. Now let's do the other part here with our sodium hydroxide, where we are looking at 0.10 molar, the millimoles over 50 milliliters. So this is just going to give us 5.0 millimoles of the hydroxide to start with. So BCA chart, we have our acetic acid reacting with the hydroxide to give us water and acetate. And for acetate, like I said, it's going to be this H right here that gets removed. That's what's going to combine to form the water. And then you have this part left over, and that would be the acetate. Writing it the organic way. Just keeping familiar with that, because I do like to use those organic compounds. So initially we have 10 of our acid, 10 millimoles, 5 of our base. Don't need to really concern ourselves with the water. 0 of our conjugate before. Now the change, looking here, the lower number being the 5 here, that's what we're going to subtract. So subtract that on the reactant side. That's what's going to be added to our conjugate, because that's how much conjugate's produced. And then we have 5 of this. This cancels down to 0. And we will have 5 of our conjugate. This is kind of interesting. We have our conjugate in solution. We have our acid in solution. So this is definitely a buffer. And we can go straight to using the Henderson-Hasselbalch equation. pH equals the pKa plus the log of the base over the acid. And they are equal here. So we know when we have equal, that means the pKa is going to be the pH. Remember, this is going to turn into the log of 5 over 5, like so, plus the negative log of 1.8 times 10 to the minus 5. So that's going to equal your pH. Because this turns into the log of 1, this part, which is 0, it cancels out. So really, the pH equals the pKa here. And that means the pH is 4.74. So remember, when you have equal amounts of your acid and your conjugate, you're going to end up, it's going to be like the midpoint of the buffer region on the titration curve, and it's going to be just the pKa equals the pH. All right. Almost done here. Let's take a look at the attacker type questions. What is the pH of a 1 liter buffer solution that is 0.45 molar acetic acid 0.85 molar sodium acetate after 0.3 moles of HCl are added. So, attacker question. Really just similar to what we've already done. All right, we're going to set up the BCA chart. We've got both things in solution, so it's a buffer. All right, so we're going to set up the BCA chart. Before change after, we're going to use the moles of our buffer, our HA and our A minus. Figure out our new concentration or moles. And we know we can use either in the Henderson-Hasselbalch equation. And that would be the last step, is using the Henderson-Hasselbalch equation. So let's take a look here and set this up. We're going to start with the BCA chart. We can easily figure out the components here. Since this is 0.45 molar and it's out of 1 liter, that is also going to be 0.45 moles of the acetic acid. And then of course, same thing here, the 0.85, that's going to be 0.85 moles of our sodium acetate, and the acetate like so here. So what we need to do here before we start plugging in everything is set up our reaction. We have our buffer and we're adding 0.3 moles of HCl. So which one's going to react with the HCl? Is it going to be the acid or the conjugate? Well, I think most of you can recognize the one that will react with the H part of the HCl is going to be your conjugate over here. So that's how we need to set up our reaction. Starting with the conjugate base, because it's going to be the one that gets, that fends off the attack of the H, and that's going to create our acetic acid, or more of it, because there's already acetic acid in solution to begin with. So before, right here, we have 0.085 moles of our acetate. We are attacking it with 0.30 moles of the H plus, and we have 0.45 moles of our acetic acid in solution here. So looking again, which one's going to be the one we look at for subtracting? The H plus is the lowest number, so it's the one that we subtract from over here, 0.3 minus 0.3 over here, but then it's going to get added over here, because every time the H plus adds to the acetate, you're going to get some more of that. And now we continue on with our after. This cancels to 0. This is going to be 0.55, and this is going to be 0.75. Oops, plus. This is not a negative, it's a plus. So now, resulting at the end here, we have both of them still in solution, the acetate and the acetic acid. So this is a buffer solution. That means we can use Henderson-Hasselbalch in order to do the pH, negative pKa, which is the negative log of the Ka, but I'm going to write it normally, log of the base over the acid. Now this, of course, is on your formula sheet. Don't forget that. It's one of the more useful ones that's on there. Now all we have to do is plug and chug. So the pH equals the negative log of 1.8 times 10 to the minus 5, since that's our Ka for acetic acid, plus the log of the base. In this case, the base is over here, so that's going to be 0.55 on this side, over the acid, which is on this side, like so. And then we go in and calculate. And it appears that this is going to give us a pH 4.61. And yes, you could compare it to the pKa here. pKa of acetic acid is 4.74, but that should make numerical sense. If you look at your ratio, you have less base, more acid. So the pH should be a little bit lower than the pKa, like so. And that would be the correct answer.